Hey guys, and welcome back to another video. In this video, we will be talking about the second part of trig identities. Alright, so let's get right into it. Okay, so there's only a couple more identities that you guys need to know. The first one is the sum and difference identities. So we'll start with that. So we'll start with the sum difference identities. Okay? So essentially, we're trying to find an identity for like sine of a plus b or cosine of a plus b, where a and b are like the angles, right? So we're trying to find an identity like that. So for sine of a plus b, this is equal to sine of a cosine b plus sine of b cosine of a. All right. And so then similarly, sine of a minus b, so that's the difference. So that's sine of a cosine b minus sine b cosine a. So notice how it's essentially the same identity. The only thing that changed is the sign in between, right? So for sine, the sign is the same as like the original one. So for example, for sine of a plus b, it's plus over here as well, and then a minus b, it's minus as well. Okay, so that's for sine, and then for cosine, we have cosine a plus b is equal to cosine a cosine b minus sine a sine b. And then cosine of a minus b is equal to cosine a cosine b plus sine a sine b. Okay, so for cosine, there's actually like a really neat trick that you can use to like remember the sum difference identities. So if you just look at cosine, you have COS, right? So what it represents is that the C means that cosine goes first, right? So like notice how in our trig identities, we have both the cosine terms grouped together first, right? So you have cosine of the first angle times cosine of the second angle. That always goes first. So that's the C in cosine is the cosine. So that goes first. And then the O, that means the opposite sign. So essentially, if you have cosine of a plus b, then it's going to be negative. It's going to be minus. If you have cosine a minus b, then it's going to be plus. So it's the opposite sign of whatever it originally was. All right. And then the S means sine. So then you're basically ending with the two sine terms together. So that's like a pretty nice way that you can remember the cosine sum difference identities. Okay. And then we'll do tangent next. So then we have tangent of a plus b is equal to tangent of a plus tangent of b all over 1 minus tangent a tangent b, and then tangent of a plus or a minus b, that's equal to tangent a minus tangent b over 1 plus tangent a tangent b. Okay, so for this one, I mean, you just have like the same sign as the original in the top, and then the denominator is like the opposite. So for tangent of a plus b, the numerator you're adding, and then in the denominator you're doing the opposite of whatever you're doing in the numerator, so you're subtracting. And then same thing for tangent a minus b. All right. So these are the six sum difference identities for the trig functions. All right. So now let's do some practice with these. Okay. So suppose I wanted you to find the value of cosine of 7 pi over 12, right? And I want the exact value, right? So you can't use a calculator. You have to use your identities or whatever. So the way you can do this is you can break up the 7 pi over 12 into two different angles for which the exact values you know. So like you already know the exact values for like pi over 6, pi over 4, pi over 3. you already know the exact values for all those. So if you can rewrite 7 pi over 12 as some combination of these, then you can just use the sum difference identities for cosine, and then you can just solve it that way. And so we can realize that we can rewrite 7 pi over 12 as cosine of pi over 3 plus pi over 4. And then we can just apply our sum identity for cosine, and you get cosine of pi over 3, cosine of pi over 4, minus sine pi over 3, sine pi over 4. And then you already know the exact values for these. So cosine of pi over 3, that's just 1/2. Cosine of pi over 4 is square root of 2 over 2. And then sine pi over 3 is square root of 3 over 2 times sine of pi over 4, which is square root of 2 over 2. So let's see, we can rewrite this as square root of 2 minus square root of 6 all over 4. So in the end, you get that cosine of 7 pi over 12 is equal to 1/4 times this quantity square root of 2 minus square root of 6. Okay, so yeah, that's the exact value. All right, let's do another example. All right, so let's do the same thing for cosine of 15 degrees. And feel free to pause the video to see if you can solve it on your own first. All right, so again, you want to try to break up the 15 degrees into other angles of the for which the exact values you already know. So we can break 15 degrees as 60 degrees minus 45 degrees, right? And then we can just apply our cosine identity, and so we will get cosine of this is equal to cosine 60 cosine 45 degrees plus sine of 60 degrees sine 45 degrees. And then cosine of 60, we know that's 1/2. Cosine of 45 is square root of 2 over 2. Sine of 60 is square root of 3 over 2, and then sine of 45 is also square root of 2 over 2. So we can get this is equal to 1/4 square root of 2 plus square root of 6 is cosine of 15 degrees. Okay, nice. All right, we're going to do a couple more examples. So next, let's so suppose you want to find the exact value of cosine alpha plus beta if cosine alpha equals negative 1/3 and cosine beta equals negative 1/4 and alpha lies in quadrant 3 and beta is in quadrant 2. All right, so to begin this problem, let's just write down the identity for cosine alpha plus beta. Right, so we know that cosine alpha plus beta, that's equal to cosine alpha cosine beta, right? Because C means we have both the cosines, and then O is opposite sign. So this is plus, I mean this is actually going to be minus. And then S means we have both the sine terms. So then we have sine alpha, sine beta. All right, so that's our identity. So we already know what cosine alpha and cosine beta is. So we already know what the first term is, but we want to know what sine alpha and sine beta is. So we also know the quadrants in which alpha and beta lie, so we can just use like our Pythagorean identities to solve for the sine alpha and sine beta. Okay, so if we were to do this, let's see, we have cosine squared alpha plus sine squared alpha is equal to 1, and you want to solve for sine alpha, so that's equal to so plus minus square root 1 minus cosine squared, and then we can substitute in cosine of alpha is negative 1/3. And we get, so this is like 8/9, I believe. Yeah, so you get that. And then alpha is in quadrant 3, so this is going to be negative. All right, and so now we need to find sine beta. So we could do the same thing for beta. All right, so now we can substitute all these values into this expression, and we'll get cosine alpha is negative 1/3. Cosine beta is negative 1/4. Sine of alpha we found is negative 2√2/3. And then sine of beta is square root of 15/4. So we can simplify this. We get 1/12 plus 2 square root of 30/12. And then just making this one big fraction, we get 1 plus 2 root 30 all over 12. Okay, so this one's a little bit more challenging problem. We have to use some of our identities that we learned in the previous video as well to help us solve this. But overall, it's the same idea, right? You just have to use your identities, and you can like solve almost any of these problems. Yeah. All right, let's do one more example for this, and then we'll move on. So, example 4. So now let's suppose you want to find the exact value of tangent alpha plus beta. If sine of alpha equals negative 1/3 and cosine beta equals negative 1/4. And they tell us that alpha is in quadrant 3 and beta is in quadrant 2. So, okay. So first, again, we have to write out our identity first to see what we're missing, right? What extra information do we need? So tangent of alpha plus beta, we know that's equal to tangent of alpha plus, because same sign, tangent beta. And then this is the opposite sign, so 1 minus tangent alpha, tangent beta. Okay, so we're not directly given tangent anywhere, right? We're only given like sine and cosine. But if we can find cosine of alpha, and then we can find tangent of alpha as well, because we know that tangent is equal to sine over cosine by the quotient identity. And similarly, for beta, if we can find sine of beta, then we can also find tangent beta, because we just do sine over cosine. So for each of these, it's pretty much the same thing again. So for sine alpha, we could just use our Pythagorean identity, sine squared plus cosine squared equals 1. And then we want to solve for cosine alpha. So that's plus or minus square root of 1 minus sine squared alpha. Substitute in negative 1/3 squared. And this is 2√2/3. Negative 2, or yeah, negative 2√2/3. All right. But remember, we don't want cosine alpha, we want tangent of alpha. So we could do sine. So we know that tangent alpha is equal to sine alpha over cosine alpha. And that's equal to negative 1/3 all over negative 2√2/3. So that cancels. So we're left with 1 over 2 square root of 2, which is equal to square root of 2 over 8, or 4, over 4. Yeah, because, yeah, square root of 2 over 4. All right, so we found tangent alpha is square root of 2 over 4. So then now you want to find tangent beta. So we could do this again for beta. So we have sine squared beta plus cosine squared beta equals 1. All right, so then again, to find tangent beta, simply we just have to do sine of beta over cosine of beta, and that's equal to negative, or square root of 15 over 4 over negative 1/4. And so that's equal to negative square root of 15. Okay, so now that we found these values, we can simply substitute them in and then simplify. So tangent alpha plus beta is equal to tangent alpha, which is square root of 2 over 4, plus tangent beta, which is negative root 15, all over 1 minus tangent alpha tangent beta. So that's square root of 2 over 4 times negative square root of 15. All right. So now comes the simplification part, which is quite tedious in this case. So first, let's just like distribute everything. So we get the following. And then let's try to get common fractions in the top and bottom. So we get let's see, square root of 2 minus 4 root 15 all over 4 over 4 plus square root 30 all over 4. Right? And so then the 4's can cancel out. So then you're left with root 2 minus 4 root 15 all over 4 plus square root of 30. But then we can't have the square root in the bottom, so we have to multiply by the conjugate of 4 plus root 30, which is 4 minus root 30. So we have to do that, and then simplifying this. Okay, this is going to be, so we have 4 square root 2 and then minus square root 60 minus 16 root 15 plus, and we can actually get a 15 out of that, so 60 root 2. I don't know if I did that correctly. And then all of that over, this is just difference of squared, so 4 squared is 16 minus 30 squared, which is, or square root of 30 squared, which is 30. So then 16 minus 30, that's just negative 14. So that should become negative 14. And so now we have to simplify radicals. So square root of 60, that's 4 times square root of 15. So square root of 60 is the same thing as 2 root 15. All right. So now we have two common denominator, or two common radicals. We can combine those. So if we come up here real quick, let's see, we have 4. So we have 4 plus 60, which is 64 root 2. And then we have negative 2 minus 16, so that's negative 18 root 15 all over negative 14. And so we could divide everything by 2. So in the end, you end up getting 32 square root of 2 minus 9 square root of 15. Or actually, you have to flip the subtraction because it's negative. So you actually end up getting, right, because the negative from the 14 flips the order of subtraction. So you get the 9 root 15 first minus 32 root 2 all over 7. All right. Yeah. Cool. All right. So now let's move on to the other identity of this video, namely the double angle identities. Okay, so double angle identities. So now we're trying to find the question, like what is sine of 2 times an angle? So the previous one was like we're trying to find sine of like some angle plus some other angle. So now we're trying to find like sine of 2 times an angle, right? So these can be derived directly from the sum difference identities. And matter of fact, like if you want to see the derivation of the sum difference identities, I'll post another video soon explaining how to derive those as well as these. So just stay tuned for those videos. But um in this video, we're just going to focus on like what they actually are. So sine of 2a is defined as 2 sine a cosine a. And then cosine 2a, this actually has 3 different like representations of it. The first one, which is like kind of like the most common, if you will, but like not really. They're all kind of like used pretty often. But the first one is cosine squared a minus sine squared a, and then this is also equal to 2 cosine squared a minus 1, and then finally it's also equal to 1 minus 2 sine squared a. All right, and then finally for tangent of 2a, this is just equal to 2 tangent a all over 1 minus tangent squared a. Okay, cool. All right, so now let's do some examples with these. So let's see, suppose we have cosine of theta equals 2/3 and sine theta is less than 0. And so then we want to find sine of 2 theta. All right. So we know that sine of 2 theta is 2 sine theta cosine theta, right? So let me write that down. Sine of 2 theta is 2 times sine theta times cosine theta. All right. So we already know what cosine theta is. It's 2/3. So now the only thing left to find is sine theta. And then once we find that, we can substitute that into this, and then we can solve. So again, we have to use our Pythagorean identities to solve for sine of theta. So we have sine squared theta plus cosine squared theta equals 1. So sine theta is plus or minus square root 1 minus cosine squared. And they actually told us the sign is negative, so this is going to be the negative square root. And if you substitute in, you get 1 minus 2/3 squared, square root all of that. And then finally, you will get, so this is 4 over 9, so 5 over 9, so negative root 5 over 9. All right, so now we can substitute that into here. So we have 2 times sine theta, which is negative root 5 over 9, times cosine theta, which is 2/3. And this simplifies to negative 4 root 5 over, oh, this is supposed to be 3. My bad. It's supposed to be 3. So all over 9. All right. Cool. Let's do another example. All right. If sine theta is equal to negative 4/5 and cosine theta is less than 0, find cosine of 2 theta and tangent 2 theta. All right. So cosine of 2 theta. So this is where like you have to choose the expression that's like most convenient. So what I mean by that is like for cosine of 2 theta, we already know what sine of theta is, right? And so if you can find sine cosine of 2 theta without finding like any other trig function, just like plugging it in, that's what we prefer. So that's why we want to use this last representation, 1 minus 2 sine squared a. Because then for that one, all you literally have to do is substitute it in and then simplify. You don't have to find like cosine theta using like some Pythagorean identity. So like the less work, the better, right? So that's why for cosine of 2 theta, I'm going to write it as 1 minus 2 sine squared theta. So that way I can just substitute directly in without having to solve for any other trig functions, which is super nice. And then simplifying this, we get negative 7 over 25. All right. And so then now to find tangent to theta. So there's two possible ways you could have done this, or you could do this. The first way is you can find sine of 2 theta, and then from there we know that tangent of 2 theta is simply just sine of 2 theta over cosine of 2 theta, and since we already have cosine of 2 theta, that's easy to evaluate. Or you can use your other Pythagorean identities to find the value of tangent of theta, and then plug that into this expression for tangent of 2 theta. However, I'm going to do the first method, namely doing sine 2 theta over cosine 2 theta, because that requires less work. So our identity for sine 2 theta is 2 sine theta cosine theta. So now the only trig function that we need to find out is cosine theta. So we have that sine squared theta plus cosine squared theta equals 1. And solving for cosine, we get negative root 1 minus sine squared. And the reason it's negative is because the problem told us that cosine is less than 0. And now we can just substitute in. So we get negative square root 1 minus negative 4/5 quantity squared. And then simplifying this, you get negative 3 over 5. Okay? Nice. And so then now we can substitute this into the sine of 2 theta expression to find sine 2 theta. And this is equal to 2 times sine theta, which is negative 4/5, times cosine theta, which we found is negative 3/5. And this evaluates to 24/25. All right, and so then we know that tangent of 2 theta is equal to sine 2 theta over cosine 2 theta. Okay, and then sine of 2 theta we found is 24/25. So we get 24/25 over cosine of 2 theta, which is negative 7/25. And then simplifying this, you get negative 24/7. All right. So yeah, that's pretty much it. So in this video, we covered the last two trig identities that you need to know, namely sum difference identities for trig functions and then the double angle identities. And like I mentioned before, I will make another video soon that discusses how to derive all these sum difference identities as well as the double angle identities. But other than that, if you enjoyed this video, please make sure to leave it a thumbs up and don't forget to subscribe. I'll see you guys in the next video.